No. It just says recording. Okay. Yeah, I'm already on it and it says mute and it has your name. And you have 3 students here. No. No, but somebody's name popped up really big. What window? It's just, okay, there's nothing. Oh, okay. What? I mean,
just so you know, you're not on mute.
you're trying to tell you. I just have to let you know. I can hear this, so just let you know you're not on camera. Okay, Mr. Younger will be here in just a second, guys. I'm so sorry.
Thanks.
I'm gonna kill you. I'm gonna kill you.
Hey, Ari. Hello, everyone. Sorry about that. Good, it's not muted. All right, so it looks like everybody's here. I apologize again for everything being late. We're going to finish up chapter 17 today. Couldn't make it this morning. I got my tooth knocked out and had to get that taken care of. See, ain't it cool? Don't it look really nice? Yeah, yeah, it's pretty hideous. So anyways, got a new one coming. And when we last spoke, we had finished up section 17.4. It's hard to talk this way too. In that, we learned about the electron volt, which basically is not only a symbol, it's a lowercase e, which is the symbol for the electron charge, and then an uppercase V, which is a sign for voltage. So it's actually not only a symbol, but it's also a formula. And it basically says that the potential energy of a charge subjected to a voltage V is QV. And that also gives us a unit. 1 electron volt is 1.602 times 10 to the negative 19th coulombs. So that's basically where we're going to start off from. But I wanted to find out, does anybody have any questions about homework problems or lab work or anything else that we talked about before this? No one? I guess that's a good sign. Let me put on the chat because I might be missing something here. Okay, so I see no chat. Yeah, we're all quiet this morning. The good news is we should be able to finish pretty quickly. I mean, I think I can still finish it well before 2:30 on this chapter, and then I'll actually, or excuse me, well before 12, and then I can just take questions and answers, work problems for y'all, anything like that that you might want to do. So if anybody doesn't have any, if no one has any questions, I am going to solve a couple problems for you, and more or less following like the textbook does. So let's get cracking with that. If you're looking at the textbook, we are, like I said, just finished chapter 7, section 17.4. We're going into 17.5, and I'll cover 17.5 through 17.9. I know I'm speaking with a lisp. I apologize. The main thing that we have to learn here is that there's yet another Coulomb's law. So we had a Coulomb's law that the force is equal to K, Q1, Q2 over R squared. And then we had another Coulomb's law that the electric field is equal to K, Q, where Q is the source of the electric field, over R squared. Well, it turns out if you do some calculus, you'll ultimately find out what the voltage is, and that voltage is K, Q over just R. So that is the voltage of at a distance R from a charge Q relative to infinitely far away from that charge. So I'm going to turn it over to the document cam, and I'll go over what we're talking about here. So we have a new Coulomb's law. Just to recap, we had from the beginning, grab the wrong pen. In the beginning, we had the force is equal to K times Q1, Q2 over R squared. That's the Coulomb force. Then we were able to come up with a concept of electric field that allowed us to get rid of the concept of action at a distance. So we were able to stop thinking that this charge here reaches out and affects this charge here without physically touching it. So we introduced the electric field, which is basically the force on a charge lowercase q divided by that charge lowercase q, and we tried to take it in the limit as that lowercase q got really, really, really small so that it didn't actually affect the electric field to begin with. So that answer, that electric field formula was K Q over R squared, where this Q is the source of the electric field. And the strength of it is inversely proportional to the square of the distance between Q and whatever particle or whatever point you wish to know the electric field. And of course, the direction, it is a vector equation, so you had to use the direction the same way we did with the Coulomb's law for the force. The force acts along a line connecting the center of charge Q1 and to the center of charge Q2. The electric field, on the other hand, acts along the line connecting the charge Q to the position P where the electric field is. So it has to act along that line, and then it's just a matter of, well, the electric field points in the direction that a positive charge would move. So now, if you actually do some calculus on this, you'd end up coming up with V is equal to K Q over, now notice this, it's just plain R, not R squared. And it's going to become more important that we use a slightly different version of K. In other words, we're going to use Q over 4 pi epsilon naught R. Well, sorry, I misread R squared there. I actually did write it for a second. So that's the new formula we're using. The voltage due to charge Q at a distance R away from Q is Q over 4 pi epsilon naught. Remember, K was 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. Now we have epsilon 0, which is that constant. That's 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. So that's the difference. Now, a student asked earlier if this K is going to change, and in some sense it does, but really we never talk about this K changing. We normally talk about this epsilon changing. So if you go somewhere that's not a vacuum or not just the atmosphere, and you're trying to calculate the voltage or the electric field or something, there's an additional factor that you multiply this by that comes into play. But you'll see that pretty much for this class, we only deal with it when dealing with a capacitor, which is something we're going to do today as well. So now here's the new constant, 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. That's that guy that goes right in there. It's called the permittivity of free space. It basically is a measure of sort of how much electric field can be held in a vacuum. Like if you were talking about in the atmosphere, if you got the electric field up stronger and stronger and stronger, at some point the electric field will become so strong that the individual atoms and molecules in the atmosphere will switch their roles from insulators to conductors, and you'll actually get a lightning strike. That is sort of a measure of the permittivity. So that's just a way of thinking about it. Now, with that in mind, we can start asking questions like, what is the potential due to a positive or negative charge at some distance away? So, for instance, let's consider a charge Q, which is equal to 44.4 microcoulombs. Okay, and let's consider it at a distance of, I don't know, let's do 0.5 meters. So that's what's going to be R. Now, the big deal here, and this is part of the reason that we switch the voltage, is this is a scalar quantity. These two guys are vectors. They have directions associated with them. This one just has a sign associated with it. It's just a number. And in fact, you need to use the sign with this one. Okay? So remember, we didn't put in the negatives in either of these charges or in this charge when we were calculating electric fields and force. With this formula, you will put in the charge. Okay? So I'd like to know, what is the electric potential? That's another word for voltage. What is the electric potential 0.50 meters away from a 44.4 microcoulomb charge? What electric potential exists at a 0.50 meters away from a 44.4 microcoulomb charge? So the formula is pretty straightforward. Really what we're doing is we're imagining basically that if you go infinitely far away from this charge, the electric potential would be 0, because obviously if you're infinitely far away, it shouldn't have any effect on anything. And then the answer would just be V is equal to 1 over 4 pi epsilon naught Q over just plain R, not R squared. Now, in this case, that's still K, so you might have guessed that's probably why I used the 44.4, and it is. So I don't have to do any math. So I'm going to write 9 times 10 to the 9th Newton meter squared per Coulomb squared. In other words, I'm putting in K instead of 1 over 4 pi epsilon naught. As Q, I'm going to write this as 1/9. Excuse me, 1/9. That would be 0.111. Times 40 would make it 1, or 4 would make it 4.44, but 40 would make it 44.44. So I want to say 40 times 10 to the negative 6 coulombs. So realizing that 4 times 1/9 would actually be 0.444, 4 times 1/9 would be 0.444. 40 times 1/9 would be 4.44. So actually I got to do 400. times 10 to the negative 6th. And then I'm going to divide that by 0.50 meters, which, by the way, is the same thing as 1/2. So dividing by 1/2 is the same thing as multiplying by 2. So ultimately what I get is this 1/9 cancels out with this 9. And these 200 here, this 400 here, ends up multiplying times 10 to the negative 6 to give me 4 times 10 to the negative 4th coulombs. So when I divide by this 1/2, it becomes multiplying by 2 up here, so that'll be 8. And then I got 8 times 10 to the negative 4th times 10 to the 9th, that'd be 10 to the 5th. So I'm going to call this 8 times 10 to the 5th volt. So that is the electric potential at that distance away. If I wanted to take a lot of distances, since this is a positive charge, I could actually make a plot of the voltage as a function of time, or excuse me, as a function of distance, R. And what I'd see is as this R gets closer and closer to 0, this thing actually approaches infinity. But as it gets closer and closer to R being infinity, it gets closer and closer to 0. So the graph should look something like this. So that's V equals Q over 4 pi epsilon naught R. If we did that for a negative Q, we would get a function that looked like this. So here's V again. And I know what it's going to look like. That's why I drew it in this weird position. This is R. Now, when R approaches 0, I still get infinity, but I get negative infinity. So it'll actually go like this. So that's what the potential looks like for Q being a negative. Anybody have any questions on that? Now, because I'm a goober, I'm going to check my math that I told you about earlier. $400 times 0.111, I want to double check. Yeah, that's 44.4. Yeah, just wanted to make sure because I first said 40 and I wanted to make sure that's right. So yeah, this math works. This does give us the electric, or excuse me, the, well, I could call it the electric potential at a distance of 0.5 meter away from a 44.4 microcoulomb charge. And notice that's a really big voltage. That's a 800,000 volts basically. Okay. Now you might be generally thinking, well, when you have a lot of volts, that's a bad thing, and it could be, but it also could be pretty innocuous. So, for instance, the Van de Graaff accelerator or generator that we use to do demos, you've probably seen them before. The big silver ball, I mentioned it last time. The big silver ball that you grab onto, and your hair will stand up really, really high. Well, that thing can often, get up to 50,000 volts. So, but still it's fairly safe because it doesn't deliver much current. The current is really the thing that kills you. It's basically pushing charges through your body and they sort of burn their way through, if you will. So it's more about the current. So don't always think that a high voltage means high current and therefore can kill you. Sometimes a high voltage is not that big a deal. Just always err on the side of safety. So that's how we got basically a positive charge. If I wanted to actually calculate this for a negative charge, really the only difference would have been a negative sign here. So if Q was negative 44.4, then the answer would have came out to negative 8 times 10 to the 5th. And technically I should call that 8.0, but anyways, it's just close enough. Okay. No questions on that, hopefully. All right, so last time we actually had worked basically a dipole. I remember telling you about the dipole and how that's sort of important. We calculated basically the electric field at some point up above a dipole, stuff like that, and it was a vector addition problem, so it's kind of a pain in the butt. Today we're going to actually do one where we're actually going to calculate the electric potential as opposed to the electric field. the electric field or the force, both of those were vector quantities. And when we worked with the dipole, we had to do vector algebra to actually figure out the answers of, you know, how large of a force was acting on a given charge, or how big of an electric field there was at a given location near the dipole. In this case, we're actually going to do it quite differently. We're going to do voltage. So let's imagine I have an X and Y axis. There's my Y axis. There's my X axis. And with the X axis, we can say, let's say, I'll do 20 centimeters on this side and 20 centimeters on this side. I think this is like what I worked before. This charge Q2 is going to be negative 4.44 microcoulombs. And this charge over here, Q1, is going to be positive 4.44 microcoulombs. And in part A, I'd like to know, let's say this distance right here is 30 centimeters. I'd like the electric potential at A. And then for part B of this problem, I'd like to know the electric potential at B, which is that point right there. Okay. So this is actually going to be unbelievably easy compared to what we've been doing. So let's first off do part A. In part A, the voltage at A is equal to the voltage at A due to 1 plus the voltage at A due to 2. Notice I didn't put any vector symbols on top, no vector arrows or anything, because these are just numbers. I just add them, okay? Of course, I do have to put the sign in. That's the big difference today, is when we're using this voltage formula, that guy, we're actually going to put the sign in, okay? So other than that, it's just a lot easier, but we do got to remember to put the sign in. So the voltage at A is actually equal to K Q1 over R1, and the voltage at A due to 2 is K Q2 over R2. Okay. Well, we know K. I'll factor that out. In fact, that's 9 times 10 to the 9th Newton meter squared per Coulomb squared. I'm going to factor that out and just leave in here 4.44 times 10 to the negative 6 coulombs. All that divided by this little distance, which is 0.30 meters. So basically 3/10. And then plus, now I've got a negative 4.44 times 10 to the negative 6 coulombs over, if you look at this is 20 plus 20, that's 40, plus this is 30, so this is a 3, 4, 5 triangle. That means this distance would be 50 centimeters. Again, I apologize for my lisp due to my missing tooth. But this is now 40 times 1/9. So the 1/9 cancels out with the 9, leaving times 10 to the 9th. I'll just write it as 10 to the 9th. Newton meter squared per Coulomb squared times 40 times 10 to the negative 6 over 3/10 minus 40 times 10 to the negative 6. Got a negative over here. All right, forgot to write it clearly. Coulombs. And this is 5/10 of a meter. So the 10 to the 9th times the 10 to the negative 6 gives me 10 to the 3rd. And then the 40 minus the 40, well, that would be fine, except for I've got different denominators, so I can't just add them. The good news is that I can multiply by 10 and then divide by 3, and I'll get 10 to the 9th. Go ahead and deal with the units. So this Newton is going to stay there. One of the meters is going to disappear. and the coulomb in the bottom, one of them will stay. So I've got that. Now I've got 400 times 10 to the negative 6 over 3 minus 400 times 10 to the negative 6 over 5. What I did was, when you divide by a fraction, you multiply by the reciprocal. So I've multiplied the 10 on top, and that's what made this from a 40 to a 400. So at this point, I could just divide those, or I could even get a common denominator. Obviously, the least common denominator would be 15. So I'll do it that way just to keep the arithmetic kind of succinct. Newton meter per coulomb, I'll discuss that unit in a second. So if I wanted to get a common denominator of 15, I got to multiply by 5 top and bottom here, and by 3 top and bottom here. So 5 times 4 is 20. So now I'm looking at 2,000 times 10 to the negative 6. And that's actually the whole answer. I don't know, it's actually now over 15. Minus this 5, this 3 times this would be 1,200 times 10 to the negative 6. And that'll also be over 15. So now I can just add those numerators. It's 2,000 minus 1,200, that'd be 800. That'd be 800 times 10 to the negative 6 fifteenths. So the 100 there is going to make this 10 to the negative 4th times 10 to the 9th. That'll be 10 to the 5th. So I get 10 to the 5th and then 8 fifteenths, which doesn't look as pretty as I would like it to be. But anyways, I'll do 8 fifteenths times 10 to the negative 6, like I said, negative 4, and that would be 10 to the 5th. And the Newton meter is a joule, if you remember from last semester. And a joule per coulomb is the volt. So that does give me the units I want. And then it's just a matter of dividing 8 by 15 and gives me 0.533. 0.533 times 10 to the 5th volts, which is also equal to about 5.3 times 10 to the, so I multiplied by 10, that means I got to divide by 10, so it's 10 to the 4th volts. So the voltage at A is 5.3 times 10 to the 4th volts, or basically 53,000 volts at A. Now at B, check this out, it actually is, life is going to get a lot easier here. So for part B, VB is equal to VB1 plus VB2. Again, no vectors. That's going to be 9 times 10 to the 9th Newton meters squared per coulomb squared. In other words, I'm factoring that K out like I did before. Now this time it's going to be 4.44 times 10 to the negative 6 coulombs over.
Professor,
Yes, ma'am.
just so you know, we can't see it very well. It's a bit blurry.
Okay, I will pull it up closer to you too, just to let you see where we're at. And when I'm done, I'll do that again. Let me see what I can do. Maybe I can put it closer. I'll just use less of the paper at a time. Can y'all see that a little better now?
It's still a bit blurry.
It's a little bit blurry. I wonder if it's a bandwidth thing.
I think it is. Like we can see like your bandwidth and like how strong your signal is.
Right.
Every time that goes down, the blurriness comes.
Goes up. So it is that. Okay. Well, hopefully the recording will look better. I got a little messy here. Let me try focus again. Okay. Well, did everybody get the description, everything I was doing here? I mean, I know I did a lot of arithmetic stuff that y'all can just sort of ignore. Or probably at this point, you're going to use your calculator anyways. But anyways, I just don't like wasting all that time doing the calculator. It's fun to do arithmetic, blah, blah, blah. But basically all I did was added the voltage due to the first charge, which would be this charge right here, times K divided by this distance right here, which is 30. It's 30 centimeters though, so I have to make it 0.3 meters. And then this charge, which is negative, only this distance from here to here was 50 centimeters, so I had to use 0.5. And then it's just a matter of doing arithmetic. And I got roughly 5.3 times 10 to the fourth. Hopefully that's right, but I literally was doing it in real time, so there's a good chance it's wrong. When I go to do point B, notice the distances are the same between Q1 and B, and between Q2 and B. So that distance is actually going to be 20, or 0.2 squared plus 0.3 squared. And then the other one will be minus 4.44. Let me put a line here so we don't get confused. Times 10 to the negative 6 over the same number, 0.20 squared plus 0.30 squared. So I think you see what's going to happen. I got 4.44 times 10 to the negative 6 over blah minus 4.44 times 10 to the negative 6 over the same blah. So the answer is just 0. Does that make sense to you guys? Now this is the same voltage that we were dealing with in lab last time, where we actually used the voltmeter and measured what the voltage was. That's the same stuff we're talking about here. And if you look at the symmetry of it, this thing has a tendency to pull a positive charge this way, whereas this thing has a tendency to push a charge that way. But they're sort of canceling each other out. In other words, I'm sort of equally distant from two sources of electric fields, but the electric field sources are oppositely charged. So that's why you end up at this particular spot getting a voltage of 0. So you can actually get near the center of and it doesn't matter what height, by the way. If you get anywhere along this line, you're basically going to get a voltage of 0. This is exactly what we found in the lab last time. We put a positive charge and a negative charge, and then we found that line dead center was 0.00 volts. Now, if I chose a point over here, that's where I got a different value, and because it depended on the distance, you would get sort of a constant around some arc. So the voltage was a constant here, and the voltage was another constant here, and a different constant here, and a different constant here. That's why we were actually able to get those field lines that sort of look like the stripes on a basketball, or the seams, I should say, on a basketball. Does that make sense to you guys now? All right, so I'll pull this closer again just to make sure everybody can see what we did. Since we had that problem. When the bandwidth went down, we had lost some of this stuff. So there's the 3 equations that we talked about. There's the 2 constants that we talked about. That's the first problem that we solved. We tried to find the voltage at a distance of ½ meter away from a 44.4 microcoulomb charge. I hate the way I talk. I did the calculation for the positive charge and got 8 times 10 to the 5th, or 800,000 volts. Obviously, that depends on R, and the way it depends on R is such that when R approaches 0, the voltage approaches positive infinity, and when R approaches infinity, the voltage approaches 0. So I got this kind of curve. Now, when we did the opposite, when I considered the voltage ½ meter away from a negative 4.44 microcoulomb charge, then I got this graph, and at least at that particular point, it'd be the exact same number, 800,000, but it'd be negative 800,000. So that was the first thing we did. Then we calculated the electric potential at 2 locations near an electric dipole. Electric dipole, remember, are basically 2 like but opposite charges separated by a distance. And I calculated the voltage at a point above one of them. And that's what's going on here. It's just numerically adding. There's no there's no vectors that you have to deal with voltage. Voltage is a scalar quantity. So the voltage at A is just the voltage at A due to charge 1 plus the voltage at A due to charge 2. So that's K Q1 over R1 plus K Q2 over R2. Notice the difference with the voltage formula. it's like the electric field, only one, it's a scalar, and two, it doesn't have an R squared, it just have an R. So basically all I do is plug in the positive charge here and the 30 centimeters here, which would be 0.30 meters, and the negative charge here and the 0.50 meters, because it had to be the distance between it and that point. And because this is a 3, 4, 5 triangle, you knew that distance would be 50 centimeters. When I did that, I came up to 5.3 times 10 to the 4th volts. Hopefully, because I did all that arithmetic without using the calculator, except for when I divided 8 by 15, and even then I didn't have to, but I know y'all didn't want to watch me do long division. Then when I did the voltage at B, that's dead center between the two, it's again the voltage at B due to 1 plus the voltage at B due to 2. In this case, the charges are opposite just like they were before, but the distances are all the same. So the distance from here to here is identical to the distance from here to here. And since the charges are equal in magnitude but opposite in charge, then these two quantities are going to add to give you 0. So the answer was 0 volts. So that's a recap of that example. Anybody have any questions with any of that? All right, so that sounds pretty good to me. Let's work another problem just so you can see what voltage does and how to calculate it. The big thing, it is a scalar quantity, but you might want to know, hey, how much work does it take to say, let's have a charge just sitting in free space, you know, infinitely far away from everything except for us, and we're not charged, so we don't matter. So we have a charge Q just sitting here. The charge Q, let's say that guy is, I like to get rid of that 9 again, so I'm going to say that's 44.4 microcoulombs. And now let's say way out at infinity, there's our symbol for infinity, way out at infinity, there's a charge of, say, 25.0 microcoulombs. Okay, now I'm going to bring it in all the way from here, from infinitely far away. I'm going to bring it in until this charge Q is 0.50 meters away. Again, it's to a ½ meter. So I'm going to bring that charge all the way into here, and I want to know what work is required. Well, you might think, well, that work is just force times distance, but the problem is the force changes. Remember, Coulomb's law says that the force is K times Q over the distance squared, but each time the distance changes, I get a different value. So in actuality, to do that calculation, you'd actually have to use calculus. But we don't, because we were actually given a formula that tells us the potential energy. The actual work is the negative in the change of potential energy. So really all we have to do is take the work to be, let's say work from infinity to 0.50 meters is actually just equal to the charge Q times the change in voltage from infinity to 0.50 meters. Your book often uses the last position and then the first position. So to make sure you knew what I was talking about, I drew an arrow in here on my subscripts just to remind you, hey, I'm starting here and I'm going here. Okay. So if I want to do this calculation, then I'm just going to say, okay, well, this is 25 times 10 to the negative 6 coulombs. That's that charge right there. And then the voltage at the, you're supposed to do always change in as final minus initial. So the voltage at the final point, which is right here, which is R, say, that's equal to the charge that caused it times K. So it'd be 9 times 10 to the 9th Newton meters squared per coulomb squared times the charge, which is 400 times 1/9 times 10 to the negative 6 coulombs. Remember, we decided that's what 4.44 was. And then all of that will be divided by 0.50 meters minus the voltage at infinity. Well, if you look at the formula is V equals K Q over R. If I let R be 1, I get KQ. If I let R be 2, I get KQ over 2. If I let R be 10, I get KQ over 10. If I let R be 10,000, I get KQ over 10,000. I think you can see bigger that gets, the smaller this voltage gets. And in fact, when it gets infinitely big, as R approaches infinity, then V is going to approach 0. So this other voltage is just going to be 0. So again, using my tricky little arithmetic stuff, I got 9, I got 1/9. I'm just pulling out everything I need, everything I've gotten in here. This 25 is the same thing as 1/4 times 100. So I'm going to write 25 as 1/4 times 100. And then I also got 100 left here and a 4 for 400. So that's all the front numbers. Then I've got times 10 to the 9th, and I've got times 10 to the negative 6. And all that will be divided by 1/2. Okay, so in other words, I'm multiplying. The reason I did this way is, notice here, this 4 is going to cancel out with this 4. This 9 is going to cancel out with this 9. And ultimately, all I have is 100, and 100 times 9 times 10 to the negative. Well, this is 10 to the 2. This is 10 to the 2. So 10 to the 2, 10 to the 2, that's 10 to the 4. Times 10 to the 9, that's 10 to the 13. Minus 6 would be 10 to the 7. So ultimately, I have the 2 comes on top, and it'll be 2 times 10 to the 7th. Work comes out in joules, which you can actually tell. The coulomb here is going to give you one of these coulombs canceling out. This other coulomb here is going to get one of those canceling out. And then a Newton meter squared. The Newton meter is a joule, but one of the meters canceled out, so that left me just a joule. So it's roughly 2.0 times 10 to the 7th joules is the work done in bringing a charge of 25 microcoulombs in to a distance of 0.50 meters. So you'll see questions like that. They'll ask you, how much work does it take to build this charge configuration? And you'll have, one charge queue that was already there, and then you bring in, say, 1, 2, or 3 other charges. Well, that's what you do. You just keep adding them up. Hey, what's the voltage now that one of the charges is in place? What's the voltage now that another charge is in place? What's the voltage now that another charge is in place? You add those, and that's the new voltage. And they originally were, 0. But when you bring in a new one, by the way, remember the new one that comes in is not just facing that one charge queue. The first one only faced that one charge queue. The second one, when it's brought in, it faces that first charge queue plus the new charge that you brought in. And when you bring in a third one's gonna actually face off against the queue that you had there originally, plus the first one you put, plus the third one you put. Plus the second one you put. So you just got to keep track of that and not double count. You'll see some examples like it, and you'll probably be asked to solve some problems like it as well. Now, the last thing we're going to talk about in terms of voltage is the voltage due to a dipole when you're really far away. So let's draw a little dipole for you guys and let you see what I'm talking about. We're going to define something called the dipole moment, by the way, and that'll make the formulas even sort of neater. So if you had a charge, let's say Q, and a charge of negative Q, and they're some distance L apart, okay? if I wanted to calculate the voltage some really far distance away here, this R is supposed to be way, way bigger than this L, which it sort of is. I mean, it's almost a factor of 10, but really the ideal scenario is at least a factor of 10. Notice the R's that you're dealing with are actually quite different there. So the voltage at this point P is actually equal to K, Q, or Q, lowercase q, over R1 minus K, Q over R2, where this is R2 and this is R1. Well, if I take a line that stops this R1 at the exact same length as R2, then I'd make a isosceles triangle more or less. Well, actually, exactly. Okay. So now I have an isosceles triangle, and this new distance, which was R2, is now going to be just plain R. And then this distance, this R1 was all this, but this R from here to here is just plain R as well. This little distance, on the other hand, is delta R. Okay. So I can now rewrite this equation and say, and I'm going to use the 4 pi epsilon naught. No, I'll keep the K. What the heck? The book's using the K too. So I'll keep the K, and I'll see K times Q. I factor out the Q. Notice it's common to both terms. So instead of R1, I'm going to say 1 over R plus delta R. And minus, instead of R2, I'm just going to say plain R. So if I wish to get a common denominator, I can make this a little more simple. So I will make a common denominator by going KQ. I'll have to multiply this one by R. So it'll be R over R plus delta R times R. That's our common denominator. Minus this one, I got to multiply by R plus delta R. So it's R plus delta R times R over R plus delta R. Okay. So in doing this, and the sign's not really going to matter here because that's always going to be taken into account, but basically what you're going to see is this R minus R just becomes 0, but the R minus delta R becomes negative K Q R, or excuse me, KQ delta R over R plus delta R times R. Again, if I'd put the negative charge over here and the positive charge over here, that sign would have been positive, so it doesn't really matter. We're just taking the magnitude ultimately. So I'm going to ignore that negative sign, even though I'll keep writing it. I'll just remind you that the end result, I'm going to get a formula that doesn't have a negative in it, and you can run with that. Now, here's the deal. If R is much, much, much greater than delta R, then R plus delta R is like adding, okay, hey, you just won, $10 million in the lottery. And then someone says, oh, by the way, that was just a round figure. You actually won $10 million plus a penny. I think you all agree that it's essentially $10 million. So that's what's going on here. We're adding a penny to $10 million. So R plus delta R is essentially equal to just plain R. So I will get negative K Q delta R over R squared. Now, if you look at this and call this angle, say here, let's call that angle theta. Actually, let's call this other one theta. Let's call this one theta right here. So then what we see is cosine theta is equal to adjacent, which is delta R, over hypotenuse, which is L. So now you can see that delta R is actually equal to L times cosine theta. So I can now write this as negative K Q times L times cosine theta over R squared. Well, that dipole moment that I told you about here it is. We're going to call it P, and it's basically the product of the charge and the distance between them. So that's the dipole moment. So what we say is the voltage at some point due to a dipole, so I'll just say dipole, is equal to K times P cosine theta over R squared. So that's another formula we will use. The dipole, by the way, is measured in units of Coulomb meters, but a more common number is called the debye or the debye, D-E-B-Y-E, and that's used for talking about the polarization or the dipole moment of molecules. And 1 debye is 3.33 times 10 to the negative 30th times 10 to the negative 30th Coulomb meters. And if you look at there's a table on page 482, table 17.2, you'll see, for instance, that the dipole moment of a water molecule is 6.1 times 10 to the negative 30th. So you can see it is right on the ballpark of the size of a dipole for an individual molecule. It has other molecules in your textbook as well. Hydrochloric acid, 3.4 times 10 to the negative 30. Amine, NH3, which would be 5 times 10 to the negative 30, so on and so forth. But that's the last topic that we're going to discuss with regards to actual voltage here. So our new formula is the voltage due to a dipole for R. Let me make a note of this. This is for R much, much, much greater than, let's say, L. So in other words, when you're really, really far away, this L is really, really small compared to the R, then you get this formula being very accurate. Any questions on that? All right, the last thing we're going to talk about in this chapter is really the capacitor. And the capacitor is kind of fun. It's pretty straightforward. It's an electronic component that stores, well, you can look at it as a charge store, but it also stores energy because it creates a little electric field inside of it, and that electric field requires energy. In fact, we'll learn that the density of energy in any given space is proportional to the square of the electric field strength. So that's what we're going to work towards. So if you imagine having a big metal plate, I should probably get it where you can actually see. I've zoomed it in closer so y'all can see. But let's take a big metal plate. And I say big because the bigger the area is, the more charge it can store. So let's take that big metal plate, and we have that connected to a wire. And now right next to it, we're going to put another big metal plate that's identical. So this is what it looks like in 3D, say. There's a wire coming from it as well. This side, if we actually connect it to a battery, say, and here's the symbol for a battery, it's either that or sometimes they'll write it like this, and sometimes they'll even do a third set. But the main thing to know about such a battery when they draw it that way is this side is the positive side and this side is the negative side of the battery. So what's going to happen is when you connect it to a battery like this, initially this battery is going to say, hey, I've got this electric field I'm creating and it's sticking inside this wire, so it's compelling all the positive charges to leave this side, so they're pushing off this way. And slowly but surely a bunch of positive charges will get on this conductive surface and actually will distribute itself uniformly over the entire surface whose area is A. So let's say the surface area is A, okay? Now, because of that, all the negative charges, remember these are conductors, so the electrons are free to move. Because of this, all the positive charges are running away from this plate, and basically all the negative charges are running towards it. So ultimately what happens is I get a bunch of negative charges stored on this plate. Now, once they reach a voltage difference, meaning you touched a voltmeter here and here, once you get a voltage equal to the voltage of the battery, then everything will stop. No more charges will flow, and that's basically how it's going to set up, okay? Well, such a thing is a capacitor, and this distance right here we'll call D. It's the separation between the plates, and in fact, the capacitance, which is the charge on the actual plates divided by the voltage across the plates, the capacitance of a capacitor is epsilon 0 times the surface area divided by D. That's the actual, two of the actual formulas you're going to need, okay? So the capacitance, which really is, like you can sell for a given voltage, say I had 1 volt. Well, if the capacitance is 1, that means I could hold 1 coulomb. If the capacitance was 2, I could hold 2 coulombs. If the capacitance was 400, I could hold 400 coulombs. So the capacitance really is a measure of how much charge it can hold. Well, it turns out that capacitance is directly proportional to A, meaning if I want to hold a lot of charge, I need to make the surface area really big. Or it's also inversely proportional to the distance between them, meaning if I really want to hold a lot of charge, I need to get the plates as close together as possible. But guess what? When you put 2 plates, even with air in the middle, which is supposed to be an insulator, when you put 2 plates really close together, there's a chance that that air is going to break down. Remember me talking about lightning? So there's a chance that the air will act enough like a conductor where the positive charges will jump the space and get in there to the negative side. At that point, you've broken the capacitor. So yes, you want to make the distance between them as small as possible, but that runs into real physical problems. If you really try to make this thing, if you got them too close together, eventually you'd see a lightning strike go from the positive one to the negative one, or actually more likely from the negative one to the positive one. So you've got some limitations on that. Plus, these are things that are put inside of, let's say, cell phones or Apple Watches and stuff like that. So they got to be kind of small. So what they end up doing is they'll take like basically 2 little sheets of aluminum foil, and they'll put some material between them called a dielectric, and then they'll roll them up like a cigarette or something. And when you roll them up like that, then you can fit them into a little cylinder, and it's really, really small, but you can fit a pretty good size area on it. And by doing that, you can get some really good size capacitances. Now, capacitance, unit-wise, the unit of a capacitance is, as you can tell, it's a coulomb per volt, which is defined to be the farad, which we just use the symbol F for. So that's the unit of a farad for capacitance. It's called the farad. And the farad's a really big unit. Like the coulomb, it's a big amount of charge. The farad is a big capacitor. In fact, if you ever walk upon a 1 farad capacitor, if the 2 terminals are not wired together, you need to be very careful of that thing, because it can actually deliver enough shock just from stored up charges it's gotten over time. It can deliver enough shock to kill you, or at least hurt you really badly. So be careful with that. Now, they do use these things, like I said, in electronic components. You can use them as surge protectors because they basically slow down the change of a voltage that they're connected to. So like if a lightning bolt happens to strike on or near a piece of electronic equipment, a bunch of current starts flowing through the wires. These capacitors can actually help refrain from jumping the voltage so high. They also can be used to store energy. So if you've ever used a 35mm camera and you take a picture with a flash, then you hear it go "vee," and it starts getting louder and higher pitched until it disappears. That's actually charging up a capacitor, because the capacitor can deliver the electricity that you need to light a flash really fast, whereas a battery can't do it that fast. So they use a battery to charge a capacitor, and then when you hit the button to take the photo, the capacitor can deliver all its charge really fast, so you get a flash. It's also used in those alternative power supplies that you have in computer labs and stuff like that, the big boxes laying down at the bottom. So if the power goes out, over several hours, the capacitor will slowly drain. But until then, it'll maintain the proper voltage and current to your computers long enough for you to save stuff and shut it down properly. So that's some uses of capacitors. As I told you, the capacitance is actually equal to the permittivity of free space. Remember that 8.85 times 10 to the negative 12th? That's that number. Now you see why we're starting to use that instead of just a K. And it's also a product of the permittivity times the area of the capacitor, surface area, divided by the distance between them. And what we can do with that is we can realize, wait a second, if I actually have a chunk of material in there, one, it gives me structural stability so that I can roll it up. Like if I just stuck these two pieces of aluminum foil next to each other and then tried to roll them, I had two conductors touching. So mechanically speaking, that can't happen. So there's one reason you have to put basically a dielectric in there from the get-go, and that's just structurally to keep the two parts apart. But it turns out that also can increase the capacitance. We'll talk about that in a second. So let's do a quick calculation. Let's see, what is the capacitance of a capacitor made of two 100 meter by 100 meter conductors one centimeter apart. So let's see, you know, let's take something that's literally 100 meters. Now 100 meters basically about, well, a meter is about 39 inches. So it's a 100 of 39 inches, which is, you know, 3,900 inches, basically on the order of maybe 110 yards. So we're talking maybe 110 by 110. So it's something about the size of a football field that's made into a square, like a soccer field, you might say. So that's a really big area, and we're only putting them a centimeter apart. So that should be something that would literally look like a big capacitance. So let's calculate it and see what it is. Well, the capacitance is equal to epsilon 0 times A over D, but epsilon 0 is 8.85 times 10 to the negative 12th. This is Coulomb squared per Newton meter squared. The area is going to be 100 times 100 is 10,000. So that's 10,000 square meters divided by 0.01 meter. Okay. Now this gets you 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. Now this 10,000 be 10 to the fourth, but this is 1/100th. That decimal there is 1/100th. So basically I could leave a 1 in the denominator and multiply that by 100. So that'd be 10 to the 6th square meters. And of course, those square meters are going to cancel out with these square meters. And what I have left is Newton per, or Coulomb squared per Newton. And I get 10 to the 6th times 10 to the negative 12th. That'd be 10 to the negative 6th. So it'd be 8.85 micro Coulomb squared per Newton. Now, that's kind of weird. It doesn't really help me very much. But I remember if I multiply this by a meter on top and bottom, I could say multiply by a meter here and a meter here. Then I haven't changed the value because I basically just multiplied by 1. So I'll say that's 8.85 micro. And now I have a Newton meter, which is a joule on the bottom, over a Coulomb times a Coulomb meter. Okay, so in other words, Coulomb squared, I'm just writing it as Coulomb times meter. But I think you know a joule per Coulomb is actually equal to a volt, so I can rewrite this as 8.85 micro times Coulomb meter over, oh, no wonder I wasn't supposed to have meters squared there. The meters were actually gone. Oh, no, I know what it is. So the Coulomb meter that's left there would be over a joule per Coulomb, but a joule per Coulomb is just a volt. Right? And, oh yeah. So yeah, this square did cancel out with that, but I still had another meter down there. So that's I didn't actually have to multiply this by meter on top and bottom. So that was my error. I knew something funny was coming up. So this meter, I multiplied by meter to get this here, but I didn't have to because remember this canceled out with that, but that didn't take care of this meter at all. So in fact, that meter was already down there. So I can fix it by just calling it like this, making that black and getting rid of this completely. So that was the unit I had originally, a Coulomb times a Coulomb. And this meter, of course, is gone right here. So I now have a, and that's gone right there. So I now have a volt in the bottom and a Coulomb on the top. So it's equal to 8.85 microfarads. Sorry about that error with the units, but I think you see, as big as that thing is, now we're literally talking about a capacitor the size of a soccer field, a big soccer field at that, separated by only a centimeter, or excuse me, by only, 1 centimeter. And even then, it only has a microfarad capacitance. So I think you can see that capacitance is hard to come by. The good news is you can actually make the capacitance even larger if you want, just by using a dielectric. So what we found by experiment is that if you replace the air or vacuum, if you replace that with a dielectric, which is just a fancy word for insulator, you get a couple advantages. So the capacitance now, once you put a dielectric in there, becomes, instead of just epsilon 0 A over D, it's multiplied by a little kappa called the dielectric constant times epsilon 0 A over D. And then sometimes, instead of using that, they'll group these two together and just call that plain epsilon with no subscript 0 on it, because the 0 means for vacuum, or at least for air, which is really close to a vacuum. So we can also say it's epsilon A over D. So this is what I was talking about earlier about if you change the space you're in, we change to epsilon instead of epsilon 0. And you can either look up this in tables or you can look up this in tables. If you look on page 485 of the Giancoli text, table 17.3 or 17-3 has a dielectric constant K, so or kappa, which is this value. And then if you multiply that by 8.85, then you get this value, which is the same as that. So I said it gives you a couple of things. Well, these kappas, for instance, run anywhere from, let's see, vacuum kappa is 1, air kappa is 1.0006. So just putting air in there doesn't make much of a difference. But if you put paraffin wax in there, you get a factor of 2.2. So your capacitance goes up by a factor of 220%. If you put polystyrene, it's 2.6. If you get really fancy, you can go to rubber and neoprene. That gives you 6.7. If you want to go to liquid water, that'll give you 80. And if you want to go to strontium titanate, that'll give you a factor of 300. So yeah, you can actually make it a lot better, meaning it can actually not only act as a mechanical barrier to keep the two plates from getting squished together by, filling it with neoprene or polystyrene or something like that. So it helps that way. But not only that, air has a breakdown voltage of about 3 million volts per meter, meaning if you have a meter separating two plates, it takes 3 million volts for lightning to strike across it. Well, when you add a dielectric, you actually get a higher electric field breakdown strength, and you get around 10 to the 6th for air. You get, and for vacuum, it was 3 times 10 to the 6th. For air, it's actually 10 times 10 to the, no, excuse me, for paraffin wax, it's 10 times 10 to the 6th. And you can even get, like for mica, you can get 150 times 10 to the 6th. So it does give you a mechanical thing to keep these from touching, but it also gives you a larger allowed electric field in between them so that the charge doesn't jump from one to the other, i.e. so the capacitor doesn't fail. So that's how adding a dielectric can help. The big thing is, though, you need to sort of understand some concepts with dielectrics. The problem solving them are just as simple as all the other ones we've done, so you don't really need to rework problems like A, E over D. You can see a ton of examples in a ton of different books. But one thing you need to be able to consider is, what if I have a charged capacitor connected to a battery? It's all charged up like that. So this is your plus side, and this is your minus side, and it's nothing but air in there. But then all of a sudden, I take a slab of dielectric and slide it in there. What's going to happen? So this is a big concept. We know that the capacitance, C, is equal to Q over V. So if I keep this battery connected, that battery has a voltage like a AA or a AAA battery has a voltage that's supposed to be 1.5 volts. When you first buy them, it's more like 1.62 or 1.63, but nominally they're supposed to be 1.5. The main thing is, though, when you connect them to something, that voltage stays 1.5 or whatever it's supposed to be. So by driving this slab in there, you're not going to change the voltage. The battery is going to maintain that unless the battery's dying. So this number's got to stay the same. But we saw that when I slide a dielectric in here, the capacitance goes up by this factor right here, whatever the dielectric constant is. And that's true, by the way. It's going to go up whether the dielectric fills the whole space or just part of the space. It's just not going to go by the whole amount if it doesn't fill the whole space. So if I slide this in here, what's going to change? Is the voltage going to change? Is the charge going to change? Is the capacitance going to change? All that good stuff. Well, we know the capacitance has to change. And since we're putting a dielectric in, it's got to go up. We know the voltage can't change because it's connected to a battery. So that means the charge must go up. So when you do this, the capacitance goes up and the charge goes up. That's kind of interesting. Why would the charge go up? Well, it turns out that this dielectric is going to become, the little molecules in it are going to become polarized so that the left-hand side of the plate looks more negative and the right, or left-hand side of the slab looks more negative and the right-hand side looks more positive. And all the little molecules in between are sort of going to line up that way so that it's negative, positive, negative, positive, negative, positive. Well, that actually creates an electric field in the opposite way. So because that electric field is smaller, or because it created electric field in the opposite direction, the electric field that's in that side of there actually decreases, and you end up getting the ability to push more charge over there. So that's one way of thinking about it. Now let's consider another example with a capacitor. This is another big concept that you got to understand. So we again have a capacitor. This time it's been charged, but I disconnected the battery. So it's just two isolated chunks of metal plate with a metal wire. And another one over here, a metal plate and a metal wire. There's your two chunks, okay? Now I'm going to take a dielectric and slide it in there. What happens now? Well, in this case, we know the dielectric coming in is going to cause the capacitance to go up. We know that capacitance is equal to charge divided by voltage. So what we conclude is that the capacitance goes up, but since the charge doesn't have anywhere it can actually go, it's not going to conduct to the non-conductor, because that's what a dielectric is an insulator. So very little, if any, charge is going to go there. So the charge is going to stay exactly the same. So this means that the actual voltage will have to go down. So those are the two big concepts. If you jab a dielectric in a capacitor connected to a battery, the capacitance obviously is going to go up, but so will the charge. If you do it when it's not connected to a battery, then the capacitance is obviously going to go up, but in this case, the voltage will drop down. So those are two big concepts everybody should know once they've had a course in physics. And you can see cool photos on the internet or even in your textbook for dielectrics and capacitors and see what they look like. If we go to actually calculate how much energy is actually stored in the capacitor, we actually come up, I don't necessarily want to derive it for you. You can see the book sort of does some hand waving, but ultimately what you find out is that the energy stored, which we'll call potential energy, the potential energy stored in a capacitor, which some books use U, some books use PE, some books just say potential energy. And here's the version I like the best because it reminds me of a spring. The energy is 1/2 CV squared. Okay. Whoa. I said it right, but I didn't write it right. It's 1/2 CV squared. If you remember last semester when we did springs, we found that the energy in a spring was 1/2 kx squared. So it is sort of like a spring, and that's the way you're going to think about it when you deal with electric circuits with these things in it. But we can, in the case that maybe we know the voltage, but not the capacitance, maybe we know the voltage and the charge, then you can use C equals Q over V to get rid of that capacitance. And when you do that, I'm going to replace this with Q over V. So I'll get Q V, because the V is going to be in the bottom. It's going to cancel out one of that. QV over 2, or 1/2 QV. That's another way of writing it. Or let's say, for instance, that I didn't know the charge, and instead I wanted to know, or instead I knew the, let's say, the charge and the capacitance, but not the voltage. I could then substitute this V, get rid of that by saying V is equal to Q over C, and in that case I get 1/2 Q squared over C. So those are the different values or formulas that you can use to find the actual energy stored in a capacitor. So it's stored basically in the electric field. The problems for this are really trivial. I don't even want to really waste your time too much, but basically if you took that capacitor that we did earlier and you put it on a voltage of, let's say, 10 volts. So let's say C is equal to 8.85 times 10 to the negative 6 farads, and the voltage is equal to 10 volts. That means the energy stored, U, would be 1/2 8.85 times 10 to the negative 12th farads, or excuse me, 10 to the negative 6. Ooh, I slipped into epsilon 0. 10 to the negative 6 farads, that's a 6, everybody. Sorry about how horrible it looks. Times V squared, that's 10 volts squared. I think you can see this is going to become 4.43 times 10 to the negative 4th joules. So that's how much energy would be stored in that capacitor that I made earlier, the size of a soccer field with a 1 centimeter distance between them. If I put it on a 10 volt battery, it would actually store basically 10 to the negative 4th joules. And remember, a joule is about as much energy as it takes to lift a red delicious apple from the ground to the top of a desk. So it's not a huge amount of energy to begin with. But when you start talking about a 100-watt light bulb, all of a sudden you say, wow, that means I can lift 100 red delicious apples from the ground to the height of a table every second. So then you start thinking, well, maybe electricity is kind of cheap. So, well, that's how you get that. Now, with that result, we can actually find something kind of neat. we can actually calculate the energy that's sort of stored up in an electric field in general, specifically the energy per unit volume in the space between the plates of the capacitor. So the potential energy between the plates of the capacitor is 1/2 CV squared. That was the formula we just used, right? Well, we know that the capacitance is equal to epsilon 0 A over D. Again, we're assuming a vacuum here, so this is something that doesn't actually have a dielectric in it. And we also know that the voltage, which is basically, remember, for a constant electric field, the voltage is equal to the electric field times the distance. That was, I think, in your book, formula 17.4. I can substitute that in for voltage, and I get ED quantity squared. So I think what you see is we have 1/2 epsilon 0. This D squared will cancel out with one of the D's here, and I'm just left with E squared from that times A times D. Well, A times D, that's the surface area of the capacitor. Remember, this capacitor right here has surface area A times the distance separation between them. That's literally the volume in the capacitor. So this is actually volume between the plates. So we ultimately say that the potential energy per unit volume is equal to 1/2 epsilon 0 E squared. So that's what I was telling you earlier, how we can find that the energy stored in an electric field goes like the square of the electric field strength. So that's another formula we can use from time to time. And that's basically it. We've completed all of the chapter. I again tell you, you should read the whole chapter 16 and 17, but my test questions, not my practice test questions, not my homework questions, but the test questions, the things that I'll actually test you on, are only from the sections that we cover. So in this case, I went 17.1 through 17.9. So does anybody have any questions? Okay, I see someone posted a question, should be 8 times 10 to the 4th. And that would have been, oh, that would have been on the other electric field probably. Marianne, can you tell me where you were talking about the 8 times 10 to the 4th? Not this one, not this one.
Yeah, sorry. It was a while ago. It was like the first problem we did, I think.
Okay.
Yeah, you had 8 times 10 to the 5th, and I got times 10 to the 4th, but I couldn't.
Oh, yeah, gotcha. Yeah, here it is right here. So according to Marianne, who I trust, obviously, 2,000 minus 1,200 should be 800, and 800 times 10 to the 6th is what we had. So that should become, I pulled the 8 and the 15 out front. That's that. And then this should have been 100 times 10 to the negative 6, which should be 10 to the 4th. So yeah, it looks like this should be 10 to the 4th. And this one, of course, would be 5.3 times 10 to the 3rd then. Thanks for catching that. I think she's right. I don't see why it wouldn't be. Yeah, that all looks good to me. So we've corrected that boo-boo. Someone asked me what's the difference between little q and big Q. So I've been trying somewhat consistently to use a big Q when I talk about a source. So if I talk about a source of an electric field, I try to use a big Q. If I talk about something being affected by a electric field, I use the lowercase q. But to be honest with you, there's nothing. I could use it. I can write the formula with a big Q or a little q. And that is often a question students always have is, you know, why the big Q versus the little q? Each instructor is a little different. A lot of instructors just like writing the little q, so they'll use little q on everything. I generally like the little q, but I like to give some emphasis to the charge that's actually creating something. So if I'm talking about voltage, like I was here, I used a big Q because that big Q is literally the reason I have this voltage. It's the source of the voltage. So I used a big Q. Whereas if I want to calculate the actual potential energy that a charged particle had at some point in this voltage, then I'd use the little q for that charged particle. Does that make sense? All right. I'll probably make some more videos. I'm hoping I'll make another video this weekend before Monday, but I might not. One thing I wanted to talk to you guys about, though, is I wanted to mention that there is a big difference between the strength of the gravitational field and the strength of the Coulomb field. So there's two ways you can think about that. Generally, what I do is I'll calculate the force due to the Coulomb field divided by the force due to the gravitational field. And one way you can think about the relative strength of them is by doing this ratio and then doing calculation for a particular problem. And whatever number comes out, that's how many times stronger the Coulomb field is than the gravitational field. So one way you can think about it is, how would each of these forces act on a unit quantity? So like when you're talking about Coulomb's law, the thing that makes the force attractive or repulsive is the charge. So that's the quantity that's relevant. In the case of the gravitational field, the thing that makes the quantity, the force relevant or makes it happen at all is the mass. So you could say, let's pretend I have a charge of 1 and another charge of 1. What's the force of the Coulomb force as a result of that if the distance between the two charges of 1 is the same as the distance between the two masses? And in that case, I'd treat the two masses as 1 and 1. So it'd be 1 Coulomb, 1 kilogram and 1 kilogram, and the distance would be equal. If I do that calculation, it's actually pretty straightforward. It's K times 1 Coulomb squared over R squared, but that R is going to be the same R I used on the bottom. So in this case, it'd be G 1 kilogram squared over R squared. I think y'all can see clearly the R squareds are going to cancel one another out. The ones are going to cancel each other out, not the units, but the ones will. So really all you get when you get this is just K over G. And K is about 9.0 times 10 to the 9th. And G is 6.67 times 10 to the negative 11th. So you'd say roughly this is about 10 to the 20th. Both of them are a big fraction of the next number up. So 9 and 7 are about the same thing. So I'm just going to call this 10 to the 20th. So in this case, you'd say, oh, the Coulomb force is 1 with 20 zeros after it, times stronger than the gravitational force. That's one way. Another way you could do it, though, is actually take a physical problem. So let's take, for instance, the force of electric attraction between the electron and the proton in the hydrogen atom. So in that case, it's K E squared over R0, which is the Bohr radius squared. But that doesn't matter because gravitationally, it's going to be the mass of the electron times the mass of the proton over that same R0 squared. So again, the R's don't come into play at all. And you get K over G, which we know is roughly 10 to the 20th. And then you get E squared over the mass of the electron times the mass of the proton, which is approximately 10 to the 20th times 1.602 times 10 to the negative 19th. That's going to be squared. The mass of the electron is 9.109 times 10 to the negative 31st kilograms. And the mass of the proton is 6.6 times 10 to the negative 27th kilograms. So I think you can see this is going to be on the order of 10 to the 20th times 10 to the negative 38. This is essentially 10 to the negative 30. And this is essentially 10 to the negative 26. So 20 minus 38 be 10 to the negative 18 over 10 30, that'd be 10 to the 56. So putting that on top, 56 minus 18 would be 46 minus 18, that'd be 38. So in that case, you get that the Coulomb force is 1 with 38 zeros times stronger than the gravitational force. So the reason we even talk about that is a lot of times students will say, well, if I use this Coulomb force to tell me how much this electron is going to accelerate, why am I ignoring gravity? Well, that's why you ignore gravity, because it's so much weaker. In fact, there's 4 forces in nature. The 4 forces are the gravitational force, which is the weakest, the Coulomb force, which is quite a bit stronger, the weak nuclear force, which I think actually turns out to be about comparable to the electric force, and then the nuclear strong force that's way stronger than the Coulomb force. The strong nuclear force is the one that holds protons up against each other in the nucleus. And as you might suspect, since all atoms except for hydrogen has an actual neutron, you might think that it clearly has nothing to do with charge, and you'd be right. And 2, you might think that it has something to do with neutrons, and you'd be right again. All right, so that's the last little bit that I wanted to go over with you guys. The rest of the time is for you to stick around, ask me questions, or you can go. I'm okay with that. I must apologize again for not showing up on time this morning. Hopefully, I've made up for it by giving you some time off and taking this question and answer session. So does anybody have any questions on anything they need help with?
I actually have a question that someone else actually posted.
Okay.
I'm just wondering, would you be able to post like the PDF version of the notes that you write, because it's a little bit blurry when we see it?
I will see what I can do. I think I can do that. I think I have most of them around, so I can take pictures and see what I can do. Okay. I actually, this document cam has a photograph mechanism, but it makes worse photographs, so I probably won't do it that way, but I can probably just take the sheets and take photographs of them, and I'll post them on Canvas for you guys.
Thanks.
No problem. Sorry about it being blurry. Anybody else have a question?
Yes, actually, do you have the master formula sheet that we would be able to use, I think, on either the test or the midterm and the final? Do you have that already?
I don't have that made up yet, but I can tell you what it's going to be made of. All the numbered equations in chapter 16 and all the numbered equations in chapter 17. So if the equation has a number next to it, like 17.9 has a number next to it, that'll be one of the equations we use.
Okay.
So that's what it's going to be, but I haven't made it up yet now. I will post the practice test. I probably won't be able to post that till Monday. And you have, of course, until Friday is when the test actually appears. And we're probably going to use that time period Friday that would normally be a lab time. We're going to make that into our test times. So you'll notice my tests tend to be on Friday. By doing that, that actually gives you time to cut out of your day that you already accounted for by being in the class. So I'll always allow you to run over so we can answer questions and stuff like that. But when you have an online test, I'm going to make it available on Friday, and you'll have at least until Monday, but usually till Wednesday to get it done. Okay.
How long are you giving us for the test?
So I usually use on the order of 4 minutes per problem. So 4 minutes per problem and 45 seconds for a concept question. And that's usually about how much time you get. So I think I told you guys I'd do 5 problems and 3 concept questions. So maybe 25 minutes, 22 minutes, something like that. It's a kind of pressed time. So if anybody has an accommodation, you got to make sure you share that with me. It'll be actually, what I'm going to do is probably, if no one has any accommodations, I'll set the time. But if someone has an accommodation, I will basically make it where y'all have to keep track of your time yourself, and then I'll just check, make sure nobody cheated. I
Is there
take off huge points
one of,
for going over.
sorry, is there going to be one of those triangle like sine cosine type questions? Because that's going to take me like 20 minutes just to do that one problem.
Okay, so you might have to do a vector addition problem, but it'll so yeah, that's a, you know, that is definitely something that's required of you. Now, using, you know, the certain triangles and stuff like that, I just want you to use your calculator and get it done as quickly as possible. But yeah, absolutely, you probably are going to have to do a vector addition problem. So I'd make sure you work a couple of those. And remember that basically what you see on the homeworks, what you see in the practice tests, and the examples in the book are usually the easiest low-hanging fruit for an instructor to pull. So you might want to make sure you can redo all those ones that you've seen as examples in the book.
Okay, would you consider giving us like an hour to take it? Because I don't know, these problems take a while to think about and to do, and it's
Yeah, I might be able to do that because because I have the midterm and the final that's going to count a lot, and those I have to watch you. The reason why I generally made it kind of tight time wise was for I don't want people just searching the internet for stuff. So yeah, I might be able to do that. What I normally do, my rule of thumb is when I make a test, I take it and then I multiply how long it takes me by 3, and that's the amount of time I give you. So I'll make that as the lowest time I'll give you, but I'll consider giving you like a whole hour.
Okay, thank you.
I just don't want y'all getting to the end of the semester and having not learned the material because you were just sort of looking up answers.
Yeah.
Then the midterm and final will kill you. So just be very careful about that. I know it's easy and tempting, and I don't even make it a rule that you can't. You actually are allowed to look stuff up. I just don't want you doing it much because it's going to bite you in the rear come midterm and final.
Yeah, I gotcha. Okay, thank you.
No problem. Anyone else? All right. Well, you folks are free to go. I'll see what I can do about making snapshots of these wonderful, horribly looking notes. But you guys have a good weekend. Stay safe. And I'll see you Monday.
Hope you're feeling better, Professor.
Thank you. Appreciate that. All right. I'm out of here.